Okay, so we are gonna begin our learning today with Dalton's law of partial pressure. And our goal is to learn this and to also learn how to do calculations with it, and then density of gas and calculations with density of gas. My plan is to go through all this material in one video for you to watch, as opposed to a bunch of different chunks. So we'll see how this goes. So some things to be aware of. Whenever we think Dalton's law of partial pressure, in a mixture of gases, when there's no chemical reaction occurring, each molecule of gas is going to act independently of each other. The volume of the gas is made up of mostly empty space. The result is that each gas exerts the same pressure on the walls of the container as it would as if it were the only gas present. Therefore, the sum of the pressure of each of the gases equal the total pressure. So when we think of that as far as a definition, this would be the definition that we want to process. This is going to turn into a mathematical equation for us. So what does that mean? The total pressure exerted by a mixture of gas is equal to the sum of the partial pressure of the individual gases. And then the formula that we would use to describe that would be as so. That the total pressure is equal to the pressure of, for example, what you're breathing in right now, nitrogen gas at that concentration, plus the pressure of oxygen that you're breathing in, plus the pressure that the carbon dioxide that you're breathing in is exerting, plus helium, methane gas, hydrogen gas, anything else that might be in the air that we're breathing in right now. So what I'm going to do is attack this problem. I'm going to go to a separate sheet of paper to do that, but we're going to look at this particular problem first and how to actually solve something like this. Okay, so I'm going to do that first classroom problem that we just saw in the notes that says a container has a mixture of oxygen, nitrogen, and helium gas, and the partial pressure of the nitrogen gas is 0.75 atmospheres. Partial pressure of the helium gas is 0.33, and the partial pressure of oxygen gas is 0.42 atmospheres. So we have PT equals the pressure of nitrogen gas that's in this container plus the pressure of helium gas plus the pressure of oxygen gas. And it doesn't matter which order we put that in. So if we look at the pressure caused by nitrogen gas alone, it says that that's 0.75 atmospheres. If we look at the pressure that is caused by the helium gas, that is 0.33. And if we look at the pressure caused by oxygen gas, that is 0.42. So we simply just, in this case, have to plug everything in. So we would do 0.75 plus 0.33 plus 0.42. So whenever I do that, and all my units are the same, so I don't have to worry about an issue with my units. I'm going to put this back over here, you can see it. So 0.75 plus 0.33 plus 0.42. And I end up with 1.5 ATM. Okay, this is going to be the most straightforward way of solving this problem. Okay, so now we are going to take a look at this problem and how would we solve something. And this is going to be probably the most complicated type of problem you're going to see. The next two example problems I think you're going to find a little bit easier. Let's go ahead and try and attack this problem. So it says, the data below describes a 2.5-liter container having the below gases with the following pressures. If carbon dioxide is added to the container until the total pressure is 623 torr and the temperature of the gas is 22 degrees Celsius, how many moles of carbon dioxide must have been added into the container? So, okay, so we're going to try that problem. And so remember some things that we already know. It's a 2.5-liter container. It's a rigid container. Okay, we already have oxygen gas in here. We have nitrogen gas in here. That's a lie, sorry. That's fluorine. We have chlorine gas in here. And we are just about to add carbon dioxide gas. Now, once that is added, we have a total pressure of 623 torr. Right now, oxygen is contributing 255 torr. Fluorine is contributing 125 torr. Chlorine gas is contributing 101 torr. And if I take that 623 and subtract all of that, I'll find out what the carbon dioxide is going to contribute as well, because they told me this is the pressure after carbon dioxide is added. So I'm going to take 623 and subtract out 125 and 255 and 101. And I end up with 142 torr. That will be the contribution that carbon dioxide is going to make. And the question is, how many moles of carbon dioxide was added? So anytime you hear moles, you got to be thinking potentially stoichiometry or ideal gas. Now this isn't a chemical reaction, so we're going to use the ideal gas equation to figure out how many moles that is. The problem is, well, and I could do this a couple of different ways. Now that I know the pressure that the carbon dioxide is exerting, then I can use that number and apply it to this equation. But the important thing to catch here is that if I use the wrong pressure value, I'm going to get the wrong answer. This 623 torr value goes for all of these gases. So if I use that value, it is going to tell me the number of moles of all of the gases that are in here. I want to use this torr value for carbon dioxide alone to figure out, well, how many moles is it just for carbon dioxide? And we have to remember to do some division here and convert this to the correct units to be able to use the ideal gas law. So 142 divided by 760 gives me 0.1868 ATM. I went right off my piece of paper. That's fine. Okay, so now I'm going to plug that in. 0.1868. This is times 2.5 is equal to n that I'm solving for times 0.08206 times, and remember they told us in the problem that the temperature is 22 degrees Celsius, but I need to change that to Kelvin, so that would become 293. So now we are simply solving for n. So we would do that number, I'm not going to plug it in again, times 2.5 divided by 0.08206 divided by 293. Okay, remember I do it a little different than you. Just old person not being able to learn new tricks. And when I do that, n value is, as you can see here, 0.0194, but for significant figures, I'm only allowed 2. So this will become 0.019. Oops, that should say moles of CO2. Okay, let's take a look at the next problem. Okay, I'm going to do both of these problems at the same time, so you see what the answer should be. This would be one you might be able to figure out. And this next one is maybe a little more complicated, but not nearly, in my mind, as difficult as the one that we just did. So I'm going to do both of these again at the same time. Okay, so I think I'm still recording here. If we look at that first example there that I said, it says if a container is filled with 3 gases, then total pressure is 1 atmosphere. What is the pressure of gas C if the combined pressure of A and B is 0.62? So we have a total pressure equaling to the pressure of A plus the pressure of B plus the pressure of C. And they just told us that the pressure of these two together is 0.62 atm. And then we were told that the pressure of the entire system is 1 atmosphere. So at this point, we have just one unknown. So 1 equals 0.62 plus the pressure of C. So this just becomes a simple subtraction of 1 minus 0.62, and we end up with 0.38 atm. Okay, and 3 significant figures to the hundredths place would be appropriate because 1.00 minus 0.62, both of those are significant to the hundredths, so our answer should be at the hundredths. So that one is pretty straightforward. Let me erase or do that. And let's take a look at this last one. So it says a tank measures 3.0 moles of nitrogen. So let's write that down. It says that for oxygen, there are 2 moles. And then for carbon dioxide, there is 1 mole. And it says if we have a container that is a fixed container and it has a total pressure of 10 atm, what is the individual pressure that is created by each one of these gases? So this is really just a ratio. If you look at all of this, what is our total amount of moles? Well, that's 6.0 moles. That's my total amount. I can use this concept to figure out how much is contributed by each of the individual gases. So if I look at nitrogen gas, well, of the 6 moles, it has 3 that contributes. So we would want to do that number times the 10 atmospheres. And that's going to tell us how much nitrogen is going to contribute. For oxygen, 2 of the 6 moles times the 10 atmosphere total. And then for carbon dioxide, 1 of the 6 moles times the 10. So when we do this, 3 divided by 6 times 10, we get 5 moles. 2 divided by 6 times 10, we get 3.33 moles, which should become 3.3 for sig figs. This should become 5.0. This should not be moles, sorry, atm. And then this last one, 1 divided by 6 times